A relation is a correspondence that to every input provides an output. So our example today is the very first day of class when I was getting to know you. I asked each student in turn to tell me their name. Okay, so I pointed to a student, they told me their name. Pointing to the student is providing the input, them telling me their name is providing the output. Now, there's a little bit of confusion inherent with this, because which name did I want? Did I want their first name? Did I want their last name? Did I want the name they happen to go by, which may not be either? Okay. So we have what's called a function, which provides a little bit more clarity. A function is a relation where every input gives only one output. So, in our example, I would change it slightly by saying I'm going to point to a student and they're going to tell me the name they go by. Okay. No confusion, the student knows exactly what name to tell me. Now, there are two other words we need with functions. The domain is the collection of all x values when we're talking algebraically, meaning we want all the inputs. And the range is the collection of all y values, which are the outputs. So the domain of our function is all the students in the room, and the range of all the functions is a list of all their preferred names. Okay, so we're going to look at two simple versions of a relation to make sure we can tell the difference between a function and a non-function. Let's look at these two examples. Okay. Every dot on the left goes to a dot on the right. I don't actually care if I'm hitting all the dots on the right in either case. The question is, which of these is a function? The top one is a function because every dot on the left, every input, goes to only one output. It's okay that some of them may go to the same output. I just care that every input goes to only one output. This one is not a function because I have this input right here that went to two separate outputs, and it causes quite a bit of confusion. In our naming example, I actually have a sister who goes by her middle name. So it causes a lot of problems because we all know her by her middle name, but occasionally she has to use her actual first name for legal reasons, and people are always confused when they say, what's her name? So, we're going to look at two graphical examples to tell the difference between a function and a not function. These are both perfectly good graphs. Here, x is the input, y is the output. Only one of them is a function, though. And we actually have a nice, pretty test that tells us which one it is. It's called the vertical line test. The vertical line test says that I should be able to draw a vertical line anywhere on the graph, and if it's a function, it will hit the graph at most once. So we look at the top graph, and imagine drawing vertical lines everywhere. Is there a single vertical line that would hit the graph more than once? And the answer is no. So this one is a function. We look at the bottom graph, and over here we're drawing vertical lines and they're doing just fine. But we get towards the middle, and all of a sudden we have vertical lines that are hitting the graph more than once. So this one is not a function. Okay. Now, there is a similar test called the horizontal line test, and it tests for something different. Okay. So we're going to look at two graphs. Notice that both of these are in fact functions. They pass a vertical line test. They do not, however, both pass a horizontal line test. Horizontal line test being that anywhere you draw a horizontal line, it should hit the graph at most once. That works for the bottom graph, but on top, we have horizontal lines that hit the graph more than once. Now, this is still a function, it just doesn't pass the more restrictive test. When a function does pass the horizontal line test, we call it 1, 2, 1, and it's going to become important later on in the semester. Now, one last thing to talk about is function notation. Okay? So when I write an equation, say y equals x plus 1, well, that's very nice to be able to graph it that way. But if I wanted to know the y-coordinate when x is 1, what would I do? I'd plug in 1 for x, and I'd get that y is 2. But when I get down to this point, it's like I've forgotten the information that this came from the input 1. So you want to know the output and also know the input that it came from. So we use something called function notation, meaning instead of writing y, we would write f of x equal to x plus 1. Okay? This means the function of x, okay, as our warning number 10. This is not multiplication, even though it looks a little bit like it. So this is not f times x, meaning I cannot separate the f and the x by dividing by one of them, say. Okay. What it means is, if I want to know the y-coordinate that goes with x equals 1, I want to compute f of 1. So I would replace every x by 1, thereby getting 2. And so my final result would be f of 1 equals 2. And in this single phrase, we have the input represented, the 1, as well as the output represented, the 2, and we didn't forget any information.